One of the continuing challenges for the structural biologist is the elucidation of three-dimensional, an appreciation of the three-dimensional structure of biological things that we look at in the microscope. Now, in some cases, one can see it all in a thin section. In other cases, these structures are so large that this is not possible. One approach is to use thicker sections, but in order to view things with thicker sections, you need an increased accelerating voltage, something like an IVEM or an HVEM. Sometimes, even with thick sections, it's not possible to encompass the whole of a structure of interest, so you need to use serial sections. So what I'm going to do in the next half hour or so is try to present to you some of the things that I've picked up over the years, some of the tips that I've gleaned from other people and learned about myself through pain and experience, things that might help you in carrying out serial section reconstruction. So much of what I'm going to be talking about isn't really my work. Some of it comes from a postdoctoral advisor of mine, Jane Westfall at Kansas State University, some from Conley Reeder's HVEM lab in Albany, some from Kent McDonald, and other people along the way. Now, may I have the first slide? Everyone should have stereo glasses, I hope. And if you don't, please get your stereo glasses. Many of the slides will not be stereo, though, as is this first slide. So this is an introduction to microscopy in the third dimension. Oh, may I have the next slide? In fact, I think I'll just wait while you get your stereo glasses. All right, I think we're all set. Well, as I alluded to, in order to image thick sections, one needs a microscope like an intermediate or a high voltage microscope. So the primary advantage of these microscopes is that due to the increased accelerating voltage, one can image thick sections without an appreciable loss in resolution. And this makes it possible then to view or image entire structures in one section. And this can be of great benefit, especially if one can use something like a selective stain or use stereo microscopy so that one can learn more and more about the three-dimensional nature of the structure of interest. Next slide, please. So why do we need the third dimension in studying structures? Well, here are three reasons. One, to correlate our ultrastructural observations with light microscopy. One, to learn about the spatial relationship. Second, to learn about the spatial relationships between organelles or structures of interest. And on a higher level of organization, to look at cell-to-cell interactions. For example, I'm a neurobiologist, and I'm very interested in the synaptic connections between receptor cells in the taste bud and the sensory nerve fibers. So using thick sections can help me to image and get an appreciation for the three-dimensional nature of the synaptic connections that I look at. Next slide. Using thicker sections provides one with distinct advantages. First of all, you can encompass more of a structure of interest in a thicker section. And one can view these sections in stereo. And for me, one of the big advantages of using thick sections is that it's very cost effective. If I can use a 1 micrometer thick section instead of a 1/10 of a micrometer thick section, that means 1/10 as many hours on the microscope, a tenth as many negatives, a tenth as many prints. So it can make it much more economical for you if the structures you're looking at can be looked at with thick sections. Next slide. So there's some additional advantages, some of which I've already mentioned. One thing that is especially significant to me is locating the needle in a haystack. It's very difficult to find synapses and taste buds. They're small structures. And if I am scanning through many, many, many thin sections, it can take a long time. But if I can go through a few thick sections, then I have a better probability of locating the structure of interest. Next slide. There are disadvantages of thick sections. One of the disadvantages is that there are more and more structures in thicker and thicker sections. And these structures can be very confounding. If you have microtubules stacked on top of a nucleus and there are mitochondria mixed in there, and you look at a single micrograph, then it's very busy. It's very difficult to interpret. So one way of dealing with this problem is to use stereomicroscopy. But that only works up to a certain level of thickness, maybe 1 to 2 micrometers at best. Above that, you can use selective staining to image the structures that you want to image and nothing else. But sometimes that's difficult. So in my case, wherein I sometimes can't use selective stains, we use serial sections. And there's a general rule of thumb in selecting the thickness of serial sections, and that is you want the sections to be thin enough so that you can look, so there won't be that much tracking in X and Y as you go through Z. So if you have a very large, smooth structure, you can use quite thick sections. If you have a very intricate structure in which it's very busy in X and Y as one goes through the Z dimension, then you need thinner sections. Next slide. Well, now this is a reminder that I'm going to switch topics a little bit and talk somewhat about embedment. You all know what that is? That's Han Solo embedded in carbonite from The Empire Strikes Back. May I have the next slide? Embedments can be a source of problems for doing serial sectioning. Those of you who have done sectioning have noticed some of the artifacts created as a result of different embedments that we use. Jim Kramer, Eileen O'Toole, and George Ray at the HVEM facility in Boulder have done a study on beam-induced artifacts in embedments. Here is an example of beam damage to an embedment, and you can see stretch marks around the region where the beam was projected onto the embedment. So not only are there marks or artifacts in X and Y, but there are also artifacts in the Z plane. That is, there is thinning of the section of the embedment that takes place in the electron beam. Now, the thinning isn't so important to those of us who are just doing serial sectioning, but for someone who's going to do a tomographic reconstruction, this thinning can be very critical and it can do some very bad artifacts. May I have the next slide? So my colleagues at the HVEM facility did some experiments on thinning and lateral shrinkage with different embedments. Now, here is an example of thinning and lateral shrinkage that takes place using the embedment LX112. Here is lateral shrinkage. There's very little lateral shrinkage. There is quite a lot of thinning, but most of the thinning takes place in the first minute. So if you're going to do tomographic analysis, it wouldn't be a good idea to use LX112. But if you're just doing a study with serial sections, LX112 might be an embedment of choice. Next slide. One of the things that I picked up at an EMSA meeting several years ago was the idea of using microwave radiation as a means of carrying polymerization to completion, as a means of stabilizing embedment. And the procedure is simply to go through the regular curing process using ovens, and then after that, to take the block and put it into a generic microwave oven. The one I use is a GE, and I put it on 10 minutes at medium-high. After that, I find that when the blocks are sectioned, the sections are much more stable. There's less compression, and as a result, we have to go to less heroic measures to relax the sections. Here is a graph showing the difference between LX112 and epochs of microwave sections. Here's LX112. There is still a lot of shrinkage. With epochs, both the lateral shrinkage and the thinning are shown here, and they're both the same. And this is important for people who want to do tomographic analysis. This is isotropic shrinkage and thinning, so that in both the X and Y and the Z plane, the shrinkage is about the same. So if you're going to do tomographic analysis, then epochs might be the embedment of choice. Next slide. Here is kind of a cartoon of several biological structures coursing throughout a chunk of tissue. And as I mentioned earlier, we have to select the section thickness that we're going to use based on the complexity of the structure of interest. If I had all of this in one chunk of tissue, then these tubules would just be kind of an electron density extending from here over to here, representing this tubule, and from there over to here for that tubule, when this is projected on a two-dimensional micrograph. So if we want to track these structures throughout the z-axis, then it becomes necessary to slice. The next slide shows another example of some of the limitations of thicker sections. Here are some structures which are bifurcating. And if we just image this as one section and then projected it onto a two-dimensional micrograph, it would be very confusing. You wouldn't recognize that these structures are dividing. So in order to resolve, to get the space resolution in the z dimension, we then need to cut sections to divide this. So you need to pick out, on the basis of the system that you're working with, you need to determine the ideal section thickness. Oh, for me, if I'm looking at the contours of a taste bud, which is a large structure, I may use 1 micrometer thick sections. If I'm going to reconstruct a cell, I may use 0.5 micrometer thick sections. But if I'm going to look at the details of a synapse, I will cut sections absolutely as thin as I can get. So even within one system, I try to tailor the section thickness to my needs. Next slide. Oh, here's a stereo pair of Janet Meal at the ultramicrotome. Now, what I'm going to say may sound facetious to you, but it's really not. There is a karma, a mindset to serial sectioning. When I'm going to do some serial sectioning, I try and psych myself up starting a couple weeks ahead of time. I try to put myself into a good mood. I try to pump myself up like an athlete getting ready for the Super Bowl. I don't have fights with my wife. I try to be a happy person in a good mood. And I pick out the cassettes I'm going to listen to while I'm sectioning and get the form bar-coded slot grids and everything all ready. If you have a sectioning room, which is kind of private, you could do your sectioning during the day. But if you're limited with space and you have to share the sectioning with some other activities in the laboratory, it might be good to do sectioning at night or on the weekend. But when I go into section, I'm ready, I'm psyched, I look forward to it. And it makes a big difference when you're ready, when you're up for it. Next slide. I attended a meeting several years ago on preparation of biological specimens, and Sita from LKB gave a presentation on care and maintenance of diamond knives. And there was quite a revelation I picked up at that. Diamond knives, as you know, have a monomolecular edge. And if one applies pressure to a diamond knife in the right plane, they're very strong. If you apply pressure to a diamond knife in the wrong plane, they're very weak. So with the edge of a diamond knife, something like this, as the section comes down, the strongest plane is where the section, where the block face meets the knife edge. So that's very strong. And the way Sid had demonstrated that, or talked about it, was moving a block over the diamond edge so that it was several meters. It was going to be a section several millimeters thick. Meters is a bit extreme. So the block was over the knife edge, and then they tapped the block, and then this big chunk of embedment fell off. And after that, they proceeded to cut several thin sections, demonstrating that the diamond was not bothered at all. Then, after that, took a piece of Ross lens tissue and dragged it across the knife edge. And the knife was ruined. So the take-home message is that the knife is very strong in this plane, but if you drag something so that you're pulling on the monomolecular edge, you're going to ruin the knife. And the damage, even if you start in one little spot, tends to spread with time. So be careful when you're using manipulator hairs and you don't drag them across the diamond edge. Next slide. As the block face comes down and hits the knife, there is an unavoidable compression of the section. This can be ameliorated in several ways. One is to use a proper embedment, which is thoroughly polymerized. And as I mentioned earlier, one way of carrying polymerization to completion is to microwave the blocks. Another thing that you can do after you've cut the section is to spread the section. In the past, people used things like trichloroethylene or xylene or other terribly toxic chemicals. And this is something we try not to do today. We use a heat pen now, and they're commonly available, and they seem to work quite well. For very thick sections, sections thicker than a micrometer, you can just pick the sections up with forceps or a manipulator hair and float it on a drop of water and then heat the drop of water, and that will help the sections to relax and spread. Next slide. The loading of the sections is a kind of an art in itself. I have learned that you can't be a coffee achiever and do this well, so that I don't have coffee or anything like that. I try to be relaxed when I'm doing this. Next slide. The standard method for loading the sections onto a grid is to just dip the grid in the boat at about a 45-degree angle, and then I would touch the last section to the grid and slowly pull the grid out, and hopefully the ribbon will adhere to it. If you're doing a series of ribbons, you can put the ribbons together and form a platform, and then try and load the whole platform at time. That takes time, and sometimes it doesn't work. Sometimes the ribbons get out of order, but there's a way to deal with that. Next slide. Something I learned from Conley Reeder is that when you are preparing your ribbons as they come off, make each ribbon one section longer than the previous ribbon. That way, the set of ribbons will be coated, so that when they're loaded onto the grid, even if they get out of order, you will know that the ribbon with 20 sections on it comes before the ribbon with 21 sections. And that's really a neat idea. It's very simple. I wish I had thought of it, but it works well. And ideally, when you do that, you'll come up with a nice grid with a lot of sections on it, as shown in the next slide. So here is a form bar coated slot grid with about 220 serial sections on it. And this is prepared by a colleague of Conley Readers, and this is like the ultimate in the art of serial sectioning. So when you can achieve this, you've made it. And I haven't achieved this yet. Next slide. After the grid is loaded with sections, you want to avoid wrinkles on the grid or on the section. A method I've used is to just put the grid into some negative action forceps and let it sit and air dry under a beaker or something to prevent dust from getting on it. Recently, I saw a little technique paper by Hildegard Crowley in which she puts the drying grids into a light vacuum. And the light vacuum, according to this paper, helps to prevent the formation of wrinkles in the sections. So that I haven't tried it yet, but it's something I'm going to try. Next slide, please. After the grids are dried, the next step is staining the grids. In the past, I used a Hiraoka stainer for staining 40 grids at a time. But for some of our serial reconstructions, we found the 40 grids at a time not to be enough. So we built our own modification of a Hiraoka stainer, which has a grid plate that holds 100 grids. And the whole staining apparatus is shown in the next slide. So here is the stainer with the grid plate, and we put the stains into blood bags that we get from the hospital. And that way the stain is never exposed to the atmosphere. We use a peristaltic pump to pump out the stain, and the bags collapse so that the stain comes out and air doesn't go in there to contaminate the stain. This way we can keep lead stain for 6 months or more when it's wrapped up in aluminum foil. Next slide. After the grids are stained, then we evaporate a light coating of carbon onto the grids to stabilize them in the electron beam, and we made a little grid holder for holding 100 grids. Next slide. Organizing, keeping records is one of those things that compulsive anal retentive electron microscopists are especially good at. And one of the things that we have done is to just create a little micrograph logbook which facilitates this. I have little slots up here so that for each grid that I look at, we can draw a picture of the locations of the sections and maybe number the sections so that later on, a year from then, if we wanted to go back to a particular grid and a particular section, we could do it with the minimum of trouble. And there's nothing really new and exciting here, but this just facilitates the record keeping, which is so important with the things that we do. Next slide. So ideally, then, you will end up with a stack of electron micrographs of serial sections. Now, in terms of what to do next, if it's a small stack, you could just lay them out on a table, and you can look at them yourself and reconstruct in your mind put together all of the sections. This is difficult to do if you get more than, say, 4 or 5 serial sections. So if you have hundreds of sections, it then becomes necessary to make some kind of a three-dimensional model so that you can integrate all of the three-dimensional information. Next slide. So one approach that we use is to use an IBM PC-based system for producing three-dimensional reconstructions from micrographs of serial sections. The software for this was written by my colleague, Dr. Stephen Young, who was at the University of California at San Diego. Next slide. So the system that we use is based on an IBM PC. The current version uses a monochrome monitor for text and a color monitor for graphics and a digitizing tablet for tracing contours off of micrographs. We are in the process of trying to update this so it can all be done on one monitor. And I hope that will be out within about 6 months. Next slide. Here is a slide of Janet Meal in my laboratory tracing contours and entering them into the three-dimensional system. Next slide. Well, there are different kinds of 3D reconstructions. The one type is a reconstruction in which you can see all of the lines associated with all of the contours. So there is no hidden line processing at all. Here's the same reconstruction with hidden line processing, such that the structure that's in the foreground, if it's covering up, if there are structures in back of it, you cannot see the contours of the structures lying in back of it. So it gives it more of a solid appearance. Next slide. This is the kind of reconstruction we get with our IBM PC-based system. This is a stacked plate reconstruction. It uses hidden lines such that with this cell from a taste bud, the cell membrane is represented by the white contours with the pink fill. And you can see that the white lines in each successive section cover up the white lines in the background. However, it's semi-transparent so that one can look inside and see the nucleus. And the nucleus consists of dark blue contours with a light blue fill. And the nucleus is hidden line with respect to itself. So it gives an appearance of solidity, but semi-transparency at the same time. The next slide. Here is the next step up in elegance. This is a reconstruction of Conley readers. This is a chromosome with a kinetochore and a microtubule passing through it. This is a reconstruction in which we no longer see the contours. We see a shaded solid. So this gives the structure even a better three-dimensional appearance. The next slide shows the next level in which we have a shaded solid which is semi-transparent. So here is a cell with a nucleus inside. So that there are different levels, different types of three-dimensional reconstructions that one can do. The last two reconstructions I've shown you require computers more in the range of a VAX or an IRIS to carry out a reconstruction like that. But the way computers are evolving now, one will be able to do something like this in a couple years with a $10,000 workstation. Now, IRIS is going to be coming out with economical workstations in the range of PC prices very, very soon. So this is something we can all look forward to. Next, I'd like to show a movie, and this movie is an animation of one of our PC-based 3D reconstructions rotating. This movie is in mono, so this shows another way of looking at a three-dimensional reconstruction. And as one of these reconstructions rotates, even though it's not in stereo, you still extract some more three-dimensional information. Roll it. Okay. Can you focus that a tad? Here is a reconstruction of part of a taste cell in white with green contours, and lying in invaginations in the cell membrane are two nerve fibers, one which is light blue and one which is dark blue. Inside the taste cell are several mitochondria. The regular mitochondria are the red contours, and there was a large mitochondrion represented in lavender. And what a movie allows you to do is to see the structure of interest from several different perspectives. And what the movie showed was that this large mitochondrion, this unusual one, passed from one nerve fiber across the cytoplasm of the taste cell to interact with the other nerve fiber. So we suspect that these unusual mitochondria, which are found only at the close appositions between the taste cell and the nerve fiber, may have something to do with a functional contact some kind of functional interaction between the taste cells and the nerve fiber, something other than a synapse. But as yet, we don't know what this interaction really is. May I have the next slide? Okay. So here is the unusual mitochondrion in close apposition with the dark blue nerve fiber. And as the reconstruction rotates around, we can see that this lavender mitochondrion passes across the cytoplasm and then interacts with the light blue nerve fiber at the top of the reconstruction. And looking at a movie of this, it brings it all home, and it brings it all home very quickly. A lot better than a stereo pair or a series of stereo pairs. Okay, would you turn off the movie, please? And may I have the lights? No, not the lights, on the next slide. So I've tried to share with you some of the ideas and some of the things that we've learned about doing 3D reconstructions. Let me give you a few caveats, though. There are many opportunities along the way to introduce artifacts and cause problems, specifically during fixation. With chemical fixation, it takes 30 to 40 seconds for the fixation process to take place. And the biochemical machinery shuts down at not all simultaneously. So there are compartments and things which are going to be moving within a cell which are going to cause artifacts. This can be ameliorated somewhat by using cryofixation, which Eileen O'Toole is going to talk about. During the dehydration step, if one uses a classical alcohol series beginning with 30%, initially your specimen is going to swell to maybe 115% of its normal size. When you get to 70% ethanol, it will be back to about 100% or its normal size. And then when you get to 100% ethanol, the structure, the block will have shrunk. So you're going to change dimensions that way. During the embedding process, well, I talked about some of the problems with different embedments associated with shrinkage and thinning. The sectioning process, we have compression which takes place. Depending upon the kind of embedment you're using, how fast you're cutting the sections, and other factors. One has to ameliorate this using chemicals or heat in order to relax the sections and get them back to their regular size. During microscopy, there are beam-induced problems, the shrinkage and the thinning and beam damage, beam tracks. If you have the beam in just one spot, that you're going to have artifacts in that spot, and these will not be the same kind of artifacts that will be in the surrounding area. So you have to be careful when you're preparing your section with the beam. Are you going to just look at one little spot, or are you going to take low mags? If you're going to take low mags, you ought to do those first, and then go in and focus the beam onto a small spot later. During the printing process, if you're doing a montage, it becomes more challenging to match up. And there are techniques for montaging, which I haven't described, but which are in the literature to facilitate the matching of sections, or the matching of micrographs within a montage. So all in all, fixed section reconstructions are very beneficial, but we have to realize that the completed product we have is not necessarily a truly accurate representation of what the biological structure really is. It's an aid to our appreciation of the three-dimensional nature of structures, but there are things which happen along the way which distort the image. And when you look at a really glitzy reconstruction, a shaded solid that's semi-transparent, you have to realize that the computer programs which produce these things tend to do interpolations and to smooth out contours, and also to smooth out data along the way, so that some of the nicer reconstructions we've made of our taste cells have removed the synapses so that they disappear. So this is one reason why if I were to produce, if I had all the computing power that I wanted, I would still use stacked plate reconstructions with a minimum of smoothing and interpolation. And then perhaps next to that in the paper, I would have a glitzy shaded solid reconstruction, which would be more for aesthetic purposes. But you have to be careful not to smooth out real data. Thank you very much. Nancy.
You mentioned that you can view the segments by light microscopy first before putting them on the cell. Is that correct?
Nancy's question was about viewing sections with a light microscope before putting them in the electron microscope. This is a technique which Conley Reeder at the Albany HVEM facility has pioneered and done a whole lot of work with. And it facilitates, well, his specialty is correlative light microscopy and electron microscopy. He puts the grid, and you can use light microscopic stains, and these will not interfere with subsequent staining, or these LM stains won't interfere with the electron microscopy.
Is your software available, and does it have some database capability?
The question was, is our PC-based software available, and does it have some kind of database capability? This software is being distributed on a nonprofit basis by the HVEM facility at the University of Colorado. And you can, there's morphometric information such as line lengths, perimeters, areas of contours, which is stored as a ASCII file within the program, and this can be printed out, and you could take it into Lotus or Excel or something like that. Is that what you meant by database? Nina?
Have you tried using the boxes-based boxes or notches
The question was, have we used any of the voxel-based imaging for viewing our data sets? We have used microvoxel from Indec Microsystems in Sunnyvale, California. They, as part of their software, they wrote a program to port our IBM PC-based software database data sets over to their software. Another company which is porting our data sets is ICAR, the Hitachi-based system developed by John Stevens. I don't know that that's truly functional yet, but they're doing that. Yes.
Two things. Just a little comment on that one. If those systems are also compatible with Lotus and you're compatible with Lotus, you can use Lotus as a pipeline, right? And go from any place to any place with your data. Every system that would be compatible with Lotus would be able to read or write a Lotus file.
The question was, if our stuff is compatible with Lotus, would it mean that it would be compatible with everything? The only part of our data set that's compatible with Lotus that goes in an ASCII file, it's not the graphics image, it's just the morphometric information, the line lengths of the contours and the areas and things like that. The file structure for the graphics images is available if you want to port it over to another computer.